A 420 mA current loop is one of the most common ways to move a measurement from the field to a control system. The transmitter measures a process variable, then represents that measurement as current. The current travels through the complete circuit and returns to the power supply. In this lesson, you will trace that loop, convert current to pressure, explain why current is preferred to voltage over industrial cable runs, and use the live zero signal to identify likely faults. A basic loop contains 4 practical elements: a DC power supply, a 2-wire transmitter, the field cable, and a receiving device such as a PLC analog input. The supply provides energy. The transmitter controls the loop current according to the measured process value. The input measures that current, while its internal resistance creates a voltage drop. The circuit must be complete. Current leaves the positive supply terminal, passes through the transmitter, travels through the cable and input, then returns to the negative terminal. If the circuit opens anywhere, current stops. The transmitter does not create unlimited voltage. It requires a minimum operating voltage, and the supply must also provide enough voltage for the input and cable. This available voltage is called compliance voltage. A useful limit is maximum loop resistance equals supply voltage minus transmitter minimum voltage minus receiver burden voltage divided by 20 milliamps. Cable resistance includes the complete outgoing and return path. Longer cables, smaller conductors, extra devices, and poor connections increase the voltage drop. For a transmitter range from 0 to 10 bar, the span is 10 bar and the current span is 16 milliamps. The relationship is linear. Pressure equals current minus 4 milliamps divided by 16 milliamps multiplied by 10 bar. At the lower range, 0 bar equals 4 milliamps. At the midpoint, 5 bar equals 12 milliamps. At the upper range, 10 bar equals 20 milliamps. For example, at 16 milliamps, subtract 4 to get 12 milliamps above 0. Divide 12 by 16, then multiply by 10 bar. The result is 7.5 bar. Retrieval checkpoint. Without looking back, state the current for 0, 5, and 10 bar. The answer is 4 milliamps, 12 milliamps, and 20 milliamps. A voltage signal is easily affected by resistance in the cable and by electrical noise coupled into the conductors. With a high impedance input, even a small unwanted voltage can change the reading. A current loop is more practical because the same series current flows through the transmitter, cable, and input. Cable resistance still matters, but it causes a voltage drop rather than directly changing the commanded current, provided the power supply has enough compliance voltage. Shielding, grounding, separation from power conductors, and correct termination are still important. A current loop is robust, not invulnerable. The lower signal is deliberately set above 0. In normal operation, 4 milliamps indicates the powered transmitter at its lower range value, that is 0 bar for this example. The extra 4 milliamps is called live zero. This gives the control system useful fault information. A reading near 4 milliamps can represent a genuine low measurement. A reading of 0 milliamps can indicate an open circuit or loss of power. Check the supply, terminals, cable continuity, fuse, transmitter wiring, and input channel before replacing equipment. Some transmitters can also report faults using currents above or below the normal range, depending on configuration. Remember the core method. Trace the complete 2-wire circuit. Read the 420 milliamp signal as the measured span. For a 0 to 10 bar range, 4 milliamps is 0 bar, 12 milliamps is 5 bar, and 20 milliamps is 10 bar. Confirm that supply voltage covers the transmitter requirement, receiver burden, and total cable voltage drop. Use the live zero to distinguish a valid low reading from a possible open circuit or loss of power. Subscribe for more industrial instrumentation lessons covering pressure, flow, level, temperature, valves, and PLCs.